Yeah. Yeah, and also like the way they style it more, like the work is very insecure and people they go to the top.
Okay, let's get started. Today we're going to be talking about Markov chain Monte Carlo, but before we do, are there any questions about the homework that's due on Thursday? More questions about that? Okay. Yeah, I mean, it's really just practice working with Stan syntax to define those functions and then applying the concepts of continuous probability. So Markov chain Monte Carlo, but before we talk about that, I have to talk about the fact that I have appearance of a conflict of interest due to working at Columbia getting grants to develop Stan, me using Stan to try to make extra money, and that you should be aware of according to Columbia University policy. So, you know, some of the examples we've done so far with natural conjugate C between priors and likelihoods, you know, we can just sort of work out what the posterior distribution is. It's in the same family of the prior, and so if we need to, we can just call an R function that draws from that posterior distribution with like parameters A star and B star or whatever. If we need draws from that posterior distribution, for example, to plug into the predictive distribution to predict, you know, how many people we predict to live in the next apartment that we go to visit, something like that. But in general, we're not going to have named posterior distribution. And if a posterior distribution or any distribution really doesn't have a name, then there isn't going to be necessarily a explicit algorithm to draw randomly from that distribution. Remember, random variable, as we defined it in the first week, is a function. And so for someone who, you know, wants to come along and propose a new probability distribution, that they want to name, you know, an essential part really of completing the definition of that random variable is to be able to program on a computer how you would draw from that distribution and have it be consistent with the PDF or the CDF or whatever other defining characteristic of the distribution that it has. So today we want to start to talk about a general procedure from which we can draw from any probability distribution, whether it has a name or not. And most of the ones that we're going to be dealing with going forward do not. And so that is going to be very useful, particularly because, you know, in these multivariate distributions, you're very almost never going to have a way to do the multivariate integral in the denominator of Bayes' rule. And so you're not going to be able to get the posterior PDF in an explicit form, even if you have an explicit form for the numerator by multiplying the prior PDF by the likelihood. So if you just have the numerator and don't have the denominator, how can you proceed? Well, you can proceed along the lines that we'll talk about this week and nevertheless obtain draws from that posterior distribution. And then you can work with the draws, which honestly is easier than working with the PDF, even when that is technically possible. So we've been, you know, dealing with draws from different distributions, but we haven't really talked about how that is done. So like when you call R norm or something like that in R, you know, how does it work? And how do you know that the numbers that come out of it really are, you know, consistent with normal distribution? And so this sort of, you know, kind of was not entirely historically accurate, but story about how these distributions came to be implemented. So like on the first day, there was the standard uniform distribution. So how do we draw from the standard uniform distribution? You can get randomness from like lava lamps and Geiger counters and all sorts of other things these days, USB keys. On most of your computers, if you got them in the last several years, Intel actually has a random number generator built into the hardware. It's not actually used by the software because it's too slow for the purposes that we're going to use it. So software actually emulates what hardware random number generator would do by defining this number k, which is like the largest unsigned integer that a 64-bit computer can represent exactly, which is like really huge. And then it draws y from a discrete uniform distribution with all the elements between 0 and k having probability 1 over k, and then just divides that by 1.0 plus k. So 1.0 turns it into a double precision number, which can be more of those can be represented on a 64-bit computer than integers can, although it's not exact. And then you just divide by 1.0 over k, and you have essentially a random draw that is a real number between 0 and 1. And that's more than good enough for our purposes to be considered a draw from a standard uniform distribution. A standard uniform has a PDF that's 1 over b minus a, where a is the lower bound, b is the upper bound. So a standard uniform distribution is a special case where a is 0 and b is 1. You can scale it up, shift it over to get standard uniform draw on some other interval, other sample space besides the 0 to 1 interval. So once we have the ability to get draws from a standard uniform distribution, then we can go about doing a lot of other things. So questions about that? So when you call R unif in R, it essentially does this. Okay, so let's say now we want to draw from some other distribution on the second day. How will we do that? So here we have the CDF, or on the x-axis we have all positive numbers. On the vertical axis we have the CDF of the standard exponential distribution, 1 minus e to the x, the negative x, one of the two. And I think that's right. Anyway, so we have a CDF here. And so a general algorithm, or an algorithm that is general but it also works in this special case to draw from this standard exponential distribution, is to first draw u from a standard uniform distribution and use that value u to go from the vertical axis here. So let's say u comes out like right there. Go over to the curve at that height and then go down to the horizontal axis. Now you have a random draw from the sample space of x. So now you have a random draw from the standard exponential distribution that's sort of generated by making a random draw from the standard uniform distribution, using that as your height, go over to the curve, down to the horizontal axis, and now you have a draw from the sample space defined by the horizontal axis here. So in this case, standard uniform, and if you wanted to multiply that by a given expectation mu, then you'd have a random draw from some non-standard exponential distribution that has expectation mu. So that, given that you can make draws from a standard uniform distribution, now we have a way to leverage that to obtain draws from standard exponential. Everyone see how we did that? All right. So this procedure is actually pretty general. It's known as inverse CDF method of sampling for from continuous random variables. And so the previous approach would give you an algorithm to draw from any univariate continuous distribution, as long as you could represent its CDF. Just draw from the standard uniform. That gives you a height over to the curve down to the horizontal axis, which gives your sample space. And now you have a random draw from whatever distribution you used for the CDF to make a curve like that. But in order for this to be an efficient algorithm, it's best to work out, if that's possible, and it not always is, what is the so-called inverse of the CDF function, otherwise known as the quantile function. So here we have a CDF function from x to the unit interval. The inverse CDF is the function from the unit interval to the sample space of x. And because the CDF is an increasing function, we know that the inverse function for it in principle exists, but it doesn't always make it easy to write down in a convenient form to work with. But the inverse CDF always exists in principle. It's a function from the unit interval to the sample space that you're trying to draw from. So in the case where we have a standard uniform or standard exponential CDF, 1 minus e to the x, well, we can invert that relationship to write x as a function of u just by doing log of 1 minus u. And so that is the inverse function that allows us to map from u to x, and that is known as f inverse, the inverse CDF, the quantile function, all different names for the same idea. So really we're just applying this transformation to a standard uniform random variable and working out what the distribution of that is. And we've now had several opportunities to derive, what the PDF of a transform random variable is. So in general, not just for this specific case of standard exponential, but if u is a random variable that has a standard uniform distribution, and x is defined by transforming that standard uniform random variable according to the inverse CDF of some distribution, then what's the PDF for the random variable x? So what two things do we need in order to figure out the distribution of a transformation of a random variable?
Scale the deviation?
No, or that's, well, you would need to know that, but that's not what I had in mind. So, what we've done before with like location and scale transformations, maybe that is what you're thinking of. Okay, if we have some like standard normal random variable, we scale it up, we shift it over, what's the distribution of the result? And when we do those things, what are like the two pieces of information that we need to multiply together in order to get the PDF for the transformed random variable? Done like 3 times now? At least. So when we did like, transforming normal into log normal, what two things did we have to multiply together in order to get the PDF of a log normal random variate?
Was it x times the expectation of x? No, x times the derivative of.
Okay, there's a derivative in there.
Okay.
That's half of them. What was the other half?
Like the chain.
Right, so we need to apply the chain rule once. We need that derivative. And we multiply that derivative by
x f of x dx.
Yeah. So we need the PDF for the thing that we know and the derivative of the transformation that maps from what we don't know to what we do know. So in this case, standard uniform, it has a PDF of 1, which is just a constant, irrespective of what u is between 0 and 1. So 1 multiplied by anything is something that we can handle. And then we need the derivative of the transformation from x to u. So if x is given by the inverse CDF of u, then how would we write u as a function of x? X is f inverse of u. What's u? F of x. So in other words, the inverse of an inverse CDF is a yes, the original function, which, well, whatever, it's f, the CDF. And what is the derivative of a CDF with respect to x? PDF. So if you transform a standard uniform random variate by an inverse CDF of some distribution, then you have 1 multiplied by the derivative of the CDF, which is just the PDF. Consequently, the PDF of x is just the derivative of whatever CDFs you're using. And so if you can write down the inverse CDF, you can use this method to get this inverse sampling method to get a random draw from any distribution just by taking a random draw from the standard uniform distribution and transforming it by the inverse CDF of whatever distribution you want. So this, for example, is how R draws from a standard normal distribution. It takes a draw from the standard uniform and then transforms it by the inverse CDF of the standard normal to get a realization from the standard normal distribution. And so this, in principle, provides a valid algorithm to draw from any continuous distribution. But if if you don't have an explicit form for the CDF, you may have to solve an equation numerically. It's actually not all that bad, but it's not something you can just do with a pencil. But for example, with the standard uniform, we do have an explicit form of the CDF that we can invert to get the inverse CDF and thus apply the inverse CDF transformation to a random draw from a standard uniform distribution in order to obtain a random draw from a standard exponential that we can then scale up by mu or whatever. And actually those distributions that we were talking about on Thursday, which I think are really easy for you to express your prior beliefs on, those were also defined in terms of their inverse CDFs. And so that's actually what makes it relatively easy. These quantile parameterized distributions, you just sort of tell it what you think is your prior median, 25th percentile, 75th percentile, and you're good to go because those are actually the parameters of that distribution. And so they kind of map on pretty well. And so with being able to draw from a standard uniform and being able to apply the inverse CDF method to draw from any distribution where we can write down the inverse CDF, and maybe somewhere we can't really write down the inverse CDF, that basically gives us a way, okay, we can draw from any univariate continuous distribution this way. There may be better ways, faster ways, more efficient ways, but this is at least a valid way, and we can conceptually build on this in order to start drawing from multivariate distributions that do other transformations or otherwise combine univariate distributions together. Questions about inverse sampling method, inverse CDF sampling method? Or what that gets us? Okay, so now we can draw from any univariate distribution. How will we draw from a bivariate normal? So we saw before the PDF of a bivariate normal distribution has 5 parameters and like a slightly longer form, but we can do some algebraic manipulations to write this in a more condensed form that reveals the bivariate normal distribution can be written as the product of a marginal normal distribution for marginal normal PDF for X times a conditional normal PDF for Y given X. And so what are the parameters of the conditional distribution then? So the conditional expectation of Y given X is written in red here. The marginal expectation plus beta times the difference between X and its expectation, where beta is equal to rho times the reciprocal of the standard deviation of Y to the standard deviation of X. That gives us the conditional expectation of Y given X, which is in general going to be different from the marginal expectation mu Y, unless rho is 0, which is to say they're uncorrelated. Then the conditional standard deviation, sigma, can be written as the marginal standard deviation of Y, sigma Y, scaled by the square root of 1 minus rho squared. Since rho is between -1 and 1, you can square it, you get something between 0 and 1 that you subtract from 1 and then take the square root. So that's going to be a number between 0 and 1. Consequently, the conditional standard deviation is less than the marginal standard deviation of Y, again, unless rho is 0, which is to say X and Y are uncorrelated. You can also think about beta as the OLS regression coefficient when Y is regressed on X. And in that sort of hypothetical regression, sigma would be the standard deviation of the error terms. And so the bivariate normal distribution is actually at the heart of regression methods. But anyway, for the purposes that we're going to deal with today, we just have to remember that a bivariate normal distribution between X and Y can be composed by taking a realization of X from a normal distribution and then using that realization of X to condition on it when drawing Y from a conditional normal distribution whose expectation depends on the realization we just got from X. Actually, the standard deviation doesn't depend on X, but it is smaller than the marginal standard. So just to review, we have ability to draw from standard uniform. We can use the inverse CDF method to draw from a normal distribution by writing out or trying to write out the inverse CDF of a standard normal distribution. We can scale a standard normal random variable by some sigma and shift it over by some expectation to get a draw from a general univariate normal distribution. And we can compose a univariate normal realization for X, condition on that when drawing from a normal distribution from Y with conditional expectation and conditional standard deviation. Now we can get a draw from the conditional distribution of Y given X, and those two things, marginal for X and a conditional for Y given X, collectively are a draw from the joint bivariate normal distribution for X and Y. Everybody with me so far? Okay. So we're sort of building up these distributions that we can draw from. And in terms of representing this in Stan, it would really just be following the previous code with maybe some slight differences from what we're doing before. One of which is this function here. I'm going to say is going to return a matrix of S draws with 2 columns. And so I'm saying the function is going to output a matrix rather than a real number or a vector. It's going to take S, which is the number of draws from the bivariate normal distribution that I want, and mu x, mu y, sigma x, sigma y, and rho all of which are scalar real numbers. Then inside the function, I initialize a matrix called draws with S rows and 2 columns. Each row is going to hold one realization from the bivariate normal distribution. I calculate my constants once outside the loop. So that's beta and sigma from the previous page. So I only need to calculate those once because they don't change when I drop into my loop. So I'm going to do a for loop from 1 to capital S, where S is the number of draws from the bivariate normal distribution that I want. I take a realization X from the marginal normal distribution mu X sigma X, and then I use that realization of X along with beta and sigma and whatnot to draw from the conditional normal distribution of Y given X. Now X and Y together are a draw from the bivariate normal distribution that I want. And so I just stick X into the first column and Y into the second column at the Sth row. After I'm done with the loop, I just return the whole matrix of draws, and I can expose this to R, get back at S by 2 matrix that has a bunch of draws from the bivariate normal distribution. And that's, on Courseworks, bivariate underscore normal RNG, because it's drawn from a random number generator, .stamp. Questions about that or how it corresponds to the previous slide? Okay, so here, for example, I'm just going to set mu x to 0, all the sigmas to 1, and put a positive correlation of 0.75. And then I'm going to draw a bunch of times from this bivariate normal distribution, each time taking 100 draws and averaging over those 100 draws to get an estimate of the expectation of X and the expectation of Y, which I know to be 0. I just want to see how accurate that would be if I took 100 independent draws from the bivariate normal and then averaged it. And so we'll use this a little bit later, but these are 100 independent draws from a bivariate normal distribution and then averaged over X and Y separately. So that so far gives us a way to build up how we can draw from a bivariate normal. And if we just wanted to draw from a bivariate normal distribution, then we should do it that way, which is going to be the best way. But we want to use that to start thinking about, well, how would we proceed to draw from some distribution where we didn't have explicit algorithms to do so? Like draw from this marginal and this conditional and this conditional. If we don't have such algorithms, how could we proceed? And one way to do that is with the so-called Markov process. So the AR1 model that we talked about, autoregressive of order 1 model that we talked about on Thursday of last week, is one example of a Markov process, albeit a linear Markov process, where in general we can think about nonlinear ones. So a Markov process is a sequence of random variables that has a very particular dependent structure to it, such that the future is always conditionally independent of the past given the present. And so any two elements of that sequence that are not adjacent to each other can be made conditionally independent by conditioning on some value between them. However, if you sort of think about the collection of that sequence of random variables as a whole, nothing is marginally independent of anything else. But we can make them conditionally independent by conditioning on an intermediate realization. So there's marginal dependence, but a particular form of conditional independence. And as it turns out, the marginal dependence gets diminished less and less for any two values in the sequence that are separated sufficiently far enough in time. But they never actually get completely independent of each other. And so we can write the conditional PDF for the sth random variable. And when we do that, we only have to condition on the s minus 1th random variable, because given the s minus 1th random variable, s minus 2, s minus 3, s minus 4, none of those matter if we know the previous one. And then we can write the joint PDF of these s plus 1 random variables as just a marginal distribution for the 0th random variable times the product from 1 to s of all these conditional PDFs. So for x sub s, conditional on x sub s minus 1. And so we have this product of s plus 1 terms that gives us a joint PDF for these s plus 1 random variables. And then the question becomes, and the answer to this question is yes, but it's not at all obvious. Can we construct a Markov process? Can we choose these conditional distributions in such a way that the marginal distribution of the last element in the sequence is the same as a target distribution that we want to draw from, or at least is that the case as capital S goes to infinity? So can we engineer a Markov process such that the last element has the marginal distribution that we want if all we supply are these sequence of conditional distributions? So can we get a marginal PDF from a bunch of conditionals? And the answer to that is basically yes. In a class like this, we're not really going to prove that this is true, although they can be proved. And if this were in the statistics department, we would probably spend like a month or so on those. We're not going to do that in this class. So all the Markov processes that we're going to talk about have been proven to be valid Markov processes. There's not really any ambiguity. Either something is proven to have these properties or it doesn't. There's no like, well, maybe it's going to have these characteristics. So anyway, the ones that we're going to do are, and given that we can get a random draw, or really what amounts to a set of draws that are random, but not independent of each other, by initializing this Markov process in a particular way, knowing that this sequence of random variables is going to converge to the distribution we tell it to. And thereby, we can get random draws from that marginal distribution by going through a long sequence of steps where we know the conditional distribution involved. So this is a very general method to obtain random draws from some target distribution that you specify, even when you don't have an explicit algorithm to do that easily, like we do for the bivariate normal. So we want to apply to some of these things in the bivariate normal case, where we know how to do it the so-called easy way by taking just one marginal and multiplying it by one conditional distribution, and then comparing that to the hard way, which is going through this long sequence of conditional steps and showing that that results in the same bivariate normal distribution that we can get explicitly. But this Markov process will allow us to proceed even in the usual case where we don't have an explicit algorithm to draw easily from some joint distribution or posterior distribution that we want. So maybe it would be more helpful to give an example. This is the first example of using Markov processes in a somewhat not really Bayesian context, but it was later used in a Bayesian context. It was actually used in the context of trying to develop atomic weapons. So the Manhattan Project, people had a bunch of researchers working on it, including Metropolis. The Hastings guy, he came along later. But the original Metropolis algorithm is sort of a special case of what's now known as Metropolis-Hastings. So suppose you want to draw from some distribution whose PDF, at least you know the numerator of, but you don't have a customized algorithm to do so like we do for the bivariate normal. So you can construct your Markov process like this, initialize your parameters to some valid values in the parameter space capital theta, and then repeat the following 4 steps s times. Draw a proposal for the parameters, which I'll call theta prime, from some distribution whose PDF is Q, that you do have an explicit algorithm to draw from, like a normal or a uniform or something easy like that. So Q doesn't have to have any particular relationship to F in order for this algorithm to be valid. So you draw theta prime, a proposal for theta, from some distribution whose PDF is Q, that's easy for you to draw from. And then you construct alpha star, which is the ratio of the target distribution's PDF evaluated at theta prime divided by the target distribution's F evaluated at theta, which was the previous step that you had theta. And then you multiply that by the ratio of the PDFs for the Q distribution. So Q evaluated at the previous value of theta divided by Q evaluated at the proposed value of theta, theta prime. And you might say, well, if I don't have the denominator of F, how can I evaluate the ratio of the PDFs? But since it's the ratio of F to F, just evaluated at theta prime or theta, the constants in the denominator of F are going to cancel each other out. So you didn't need them in the first place. So like 82% of great mathematical advances involve canceling out the thing you don't know how to do. And that's basically what happens here. The constants in Q are not needed either, again, because it's a ratio, just evaluated theta in the numerator and theta prime in the denominator. So that gives you alpha star, or that gives you the ratio. You can say what's the minimum between 1 and that positive number given by the ratio of those 4 terms there. And then in step 3, if alpha star is greater than a realization from a standard normal distribution, set the current value of theta equal to the proposed value, theta prime. If alpha star is less than a realization from a standard uniform distribution, then keep theta the same as it was the previous step in this Markov process, and then store in the 4th step, or the 4th step within the sth step, store theta, which could be either your previous value of theta or your proposed value of theta, depending on alpha star and your realization from the standard uniform, as the sth draw in like your S by whatever K, let's say, matrix that's holding these draws from the posterior distribution. And you just repeat those 4 steps S times, and then the S draws that you have obtained by this process are going to have the PDF that you specified, or at least the numerator of the PDF that you specified, and you didn't need the constant in the denominator or any other constants in order to accomplish this. So all you needed was the kernel of the PDF of the distribution that you want to draw from. So that's great. We have S draws from this posterior PDF. But the catch is these S draws are not independent of each other. They're explicitly dependent on each other because this is a Markov process. So that's not quite as good as having S independent random draws, but at least we have S draws that we can use to describe the posterior distribution that we want without being bogged down by the fact that we can't calculate the denominator of Bayes' rule in any sort of useful form, particularly when there are multiple parameters in theta. And so that's the formula or the steps for Metropolis-Hastings. If the ratio of Q at theta divided by Q at theta prime is 1, which is to say the Q distribution that you're drawing from is symmetric, whether you evaluated at theta or theta prime, then that special case is called Metropolis Markov chain Monte Carlo. And that's the one that the Metropolis guy actually came up with around 1949. But it was published in like physics journals. And so no social scientists or anyone normal really read about this until the 1980s, or was able to apply it for anything that social scientists might be interested in until like 40 years later. But it was sort of known among the Manhattan Project people and, you know, maybe some other kind of theoretical physicists, even before they had like real computers. Really, they had primitive computers, but it was good enough for this. But it was really not until we sort of had, you know, computers in every office in every house that these sorts of Markov chain Monte Carlo methods like this, and another one which we'll talk about, started to take off and started to be useful for drawing from these, you know, posterior distributions that we might want to construct as social scientists. Now, for historical reasons, Metropolis-Hastings algorithm is very important. You shouldn't use it. It's not the best algorithm, but for historical reasons and because it's easy enough to understand, you know, we'll cover it briefly. But sort of the limitation of it is it's not a very efficient approach. So just briefly, and hopefully this is small enough or big enough for you to see. If not, you can see it on Courseworks. I've defined binormal LPDF. So LPDF means log of PDF function for the bivariate normal PDF. That's going to take a row vector as its first argument, binding together x and y. So in the Stan language, it distinguishes row vectors, which are oriented horizontally, basically, from regular vectors, which are oriented vertically. So here I'm saying I'm going to have a row vector of size 2 that's going to hold x and y, and that's going to be the first argument to the binormal LPDF function that I'm going to need to pass to my Metropolis-Hastings sampler. I calculate my constants, beta and sigma, and then I just evaluate the bivariate normal log PDF using marginal normal PDF for x and a conditional normal PDF for y given x. And I don't have to write those out because, you know, the PDFs for a bunch of distributions are already programmed into Stan, and they have like some name underscore LPDF for log of PDF. Remember, when we're doing stuff with Stan, we typically always want to work with log units. And if for whatever reason we don't want to work with log units, we start out with log units and then do e to whatever that is in order to get rid of the log units, put it back in probability units. And so these functions that end in LPDF or LPMF, if it was a discrete random variable, can be written with the statistics notation like these vertical bars here. So this is just saying xy, the first element of it, which is x, give me the log PDF of that given mu x and sigma x, and then add on to it, because we're in logarithms, the normal LPDF evaluated at y, which is the second element of xy, with expectation, conditional expectation, mu y plus beta times the residual on x, and sigma, which I previously calculated to be the conditional standard deviation. So that's just implementing the PDF for the bivariate normal that we saw before. There's no normalizing constants that I have to worry about here, but if I did, I could just ignore them when calling my Metropolis RNG function, which does Metropolis sampling. So this is going to return a matrix of S by 2 draws. It's going to have, you know, all these parameters to the normal distribution, and it's going to give me back draws from the bivariate normal. I have to initialize x and y before the loop, so they have persistence. This is a little bit different from R. So when you drop into a loop, it's going to delete everything that was inside the loop when the loop is over with, except things that were declared before the loop was done the first time. So I'm going to loop from 1 to S. Here I'm going to use the uniform distribution as my Q distribution because it's easy for me to draw from. There's one tuning parameter that I can set, which I call half width here, which is basically half the width of this uniform distribution that I'm drawing proposals from. So I draw a proposal of X called X underscore from a uniform distribution that's centered at my previous value of X and goes out equally far in both directions. And I also draw a proposal of Y underscore from a uniform distribution centered at Y. Then I construct alpha star by just doing calls to the bivariate normal LPDF that I defined previously, evaluated at the proposals, X underscore and Y underscore, and then subtract, because we're in log terms, the bivariate normal log PDF evaluated at X and Y. And so that basically gives me, so Q over Q is just 1 in this case, so I don't have to worry about that. And then I have the logarithm here, so it's a difference in logarithms. So that gives me the logarithm of alpha star. I EXP that up to get regular alpha star. I check whether alpha star is greater than a realization from a standard uniform distribution. If so, I change X to X underscore and Y to Y underscore. If not, I just leave X and Y the same as they are and go on to the next iteration of the loop. Irrespective, I'm going to store X and Y in the sth row of my matrix, and then when I'm done, I'm going to return that S by 2 matrix of draws from the distribution that I told it to draw from using this Metropolis process. So that is an example of how to use Metropolis sampler, albeit one that you don't need to know that well because you shouldn't use it, but is sort of the simplest example of a Markov chain process that we can use to draw from other distributions that are more interesting than this one and one that we could do in better ways. Anyway, I expose that to R, and what I do here is draw, so repeat this process 26 times, because 26 is the most I could fit on one slide, calling my Metropolis thing to run for 1,000 draws with the parameters that I tell it, and my half width of 2.75, which is like a tuning parameter that I played around with to get the best results. Anyway, do that whole process 26 times, so obtain like 26,000 draws from a bivariate normal. That goes all really fast, and each time I get a new batch of 1,000 draws from a bivariate normal, take the means with respect to X and Y, and now I get these two means that I can compare to the true means, which are just 0 for X and 0 for Y. So store that, print that all out, and you can see that the numbers are basically in the vicinity of 0. So these estimates of the expectations are usually like maybe a little bit more than 0.1 at the most, but usually like correct to 1 digit, maybe 2 digits, etc. So this is only 1,000 draws, but it's not a perfect estimator. These are not all like exactly 0. And that's because not only is there randomness, but there's also dependence in the randomness. So it's a decent estimator with 1,000 draws, but it's by far not perfect. If I compare that to doing the same things but drawing 100 times independently of each other from the bivariate normal algorithm that we constructed explicitly by drawing from a marginal and then drawing from a conditional given the marginal, we can see that the estimates are also like in the vicinity of 0. They're about as good as my estimates that I obtained from this Metropolis process. But when I did the independent draws, I only took 100. When I did the Metropolis, which gives me dependent draws, I took 1,000. And so my 1,000 dependent draws from a Metropolis process estimated the true means, which are 0 in both cases, about as well as 100 draws that I averaged over when I took those 100 draws independent of each other. So we're in a situation in which 1,000 dependent draws give us about the same accuracy as 100 independent draws when I'm taking the means of both times. And that's due to the fact that Markov process has dependence among the draws, and so it's a less efficient estimator. In this case, we can say it's about 10% as efficient as getting independent draws, because 100 independent draws is just as accurate as 1,000 dependent draws. Everybody see that these means estimated up here from this 26 runs of the Metropolis process are roughly about as accurate as these 26 sets of means that I got from making independent draws from the bivariate normal distribution and then averaging those, because that's a really important point. What we gain in generality by being able to use these Markov processes to draw from any distribution, sort of, the cost to that is it's not as efficient in terms of estimating these things as it would be if we could get independent draws. So dependent draws are not as good for estimating as independent draws, but it's better than nothing if you don't have a way to obtain independent draws. Does everybody understand that reasonably well? Yes.
I have some questions about the Markov process.
So do you say that like the initial random variable, like the x0 is from some known distribution, and then like you keep drawing and then the distribution evolves? So in the end one, it's the target distribution, but how do you know like where to end? That's a question.
So that's a good question. In principle, it doesn't matter what distribution you started from, like x0, as long as that has the same sample space as the distribution you're trying to draw from, it will still get there eventually. Now, the question is, what is a big enough S is a much harder question to answer, and certainly really can't be answered in general. And the reason why you don't want to actually use this Metropolis thing is because there's pretty much no safe finite value of S where you can know in advance, like, this is good enough. But we do know that it converges to the distribution we specify as S goes to infinity, but there's really no safe finite version of S. Now, in this case, it worked okay with 1,000 draws, but this was not that complicated a case. We just had 2 dimensions to the distribution they were trying to draw from, and it was only 10% as efficient as independent draws. If you start doing, 3, 4, 100 parameter models, it gets much worse very quickly. And so you'll often see people do S of like 1,000,000 or something like that, because it's so inefficient that they need to do like 1,000,000 dependent draws, and they think, oh, well, 1,000,000 is a big number, surely that's enough. But there's really no safe finite number in a lot of cases, which is why this shouldn't really be used. We can see this idea a little bit more clearly by looking at evolution of this Markov process over the 1,000 draws. So I just take one more using the same parameters that I used before. And you can see if you ask for the number of unique draws, it's only 236 in this case. So I did 1,000 draws, but only 236 of them were unique, which means more than 3 out of 4 times it was not accepting the proposal, and it was just keeping the previous realization of X and Y as the current realization of X and Y, because alpha star was less than a realization from a standard uniform. So basically 3 out of 4 times, it wasn't moving at all. It was just keeping the same draw. And so you can sort of see why 236 would be sort of upper bound for the precision that you could get. But even that upper bound is not really achieved, because even when it does move, the way in which it moves is dependent on the previous realization of X and Y. So nothing is independent of anything here marginally, although they are conditionally. And then when you look at one of these time series plots, you can see it goes for like stretches of 50 or maybe more steps where it just doesn't move. And when it does move, it's in a real sort of jaggedy fashion on both X and Y, and that's reflecting the dependence among adjacent draws in a Markov process. And so when you don't have that many unique draws, and even the ones you do have are sort of highly dependent on each other, it makes the estimation of the means less efficient. Indeed, it's only about as efficient as you would get from 100 draws independent from independent draws from a bivariate normal distribution. And so this lack of uniqueness and also the dependence among draws, even when they are unique, is what's responsible for, if you only do a finite number of draws, the inefficiency you get when estimating some of these means. And this is why you don't really want to use Metropolis, although like I've seen the Federal Reserve do this, and it's like scary. But anyway, we'll learn better stuff. So that brings us to the idea of effective sample size of a Markov chain. And so this is a very important concept that we've already alluded to, but this is kind of the technical definition. If a Markov chain mixes fast enough, where you can understand mixing as like how fast it goes through its sample space. So this is a not very good mixing represented here, because it can't really go from like one side to the other very quickly. It has to take like a lot of steps to kind of get from, let's say, here, which we'll call the left edge, to like here to the right edge. It takes it a bunch of steps to get there. And so this is not great mixing. But if a Markov chain mixes fast enough, and it can be very difficult to verify whether this is indeed the case, but if it's fast enough, then a so-called central limit theorem for Markov chains holds. And if that's true, you can calculate or estimate the effective sample size, which will be denoted N_EFF, as S, the total number of draws that you obtain, divided by 1 + 2 times the infinite sum of the kth order autocorrelation. So the correlation ex ante between 2 draws of the Markov process that are k steps apart. So if it's mixing fast enough, we can do a central limit thing to estimate the effective sample size as S divided by 1 + 2 times this infinite sum thing. And so if all these rows were 0, then it would just be the infinite sum of 0. 2 times 0 is 0. We'd be left with S/1. And the effective sample size would be equal to the total sample size. And in which case, the Markov chain Monte Carlo standard error would be the same as the standard error that you probably heard about before for like in other classes, that you found the standard error was like sigma divided by the square root of n. Well, in this case, it's sigma divided by the square root of the effective n, where the effective n corresponds to this formula here. And so when we go to estimate these rows in a Markov process, they can't all be 0 because there's correlation, there's dependence among draws that are like kind of near each other. The dependence dies out, so this infinite sum does converge to a finite number if the Markov chain Monte Carlo theorem holds, central limit theorem holds, but we don't know how fast. And so in general, those autocorrelations are going to be like positive numbers, and we can estimate this. But if you do 2 or 1 plus 2 times the sum of a bunch of positive numbers, you're going to get something that's greater than 1. And so you're dividing S by something that's greater than 1. And so in general, the effective sample size for like one of these Metropolis-Hastings things is going to be less than the nominal sample size S. And that tells you basically, you know, what I said before, that your S dependent draws are as good for estimation purposes as NF independent draws. And so if you were to like buy them on eBay, like the price of S dependent draws would be equal to the price of NF independent draws if it were possible to obtain independent draws, which it oftentimes is not, but we can take our S dependent draws and like estimate what the effective sample size of those are in terms of their efficiency for estimating the mean of the random variables that we're drawing from. And for the Metropolis sampler that we just saw the example of, the effective sample size was going to be about 100 on both the X and Y dimensions, so 1/10 of the nominal sample size. So you'd be indifferent between 100 independent draws and these 1,000 dependent draws in terms of estimating the expectation of the random variables that you're trying to draw from. And so this 10% is like, okay, barely in this example, but like I say, the ratio of effective sample size to nominal sample size gets much worse very quickly if you have a more complicated distribution that you're trying to draw from than this one, which is bivariate normal, which is like the most well-behaved two-dimensional distribution. Like what if you were trying to do this with 1,000? It would just be like a disaster. The effective sample size would be pretty much 0, regardless of how big you make S. So that's why you don't want to use these that much. Yes, Keith.
Just have a question. Where is K reference from, or what is it reference to? Is it like the minimum maximum of the sample space area?
Little k?
Yeah.
Yeah. So let's say I'm talking about the 200 and the 600. So K would be 400 in that case. Those two are 400 steps apart, but they're indexed by S. So like Y 200 would be this, and Y 600 would be that, and K would be 400, the number of steps apart that they are. Well, it's defined as the difference between two values of little s, whatever it is. So I can have the first order autocorrelation between adjacent draws in the process. I can have the second order autocorrelation between draws that are separated by 1. I can have the third order autocorrelation between iterations that are separated by 2. And this formula for effective sample size, which like I said, the computer will estimate this for you, is defined as the infinite sum of all of those autocorrelations from the first order up to the infinity order. So we're going to need these to like diminish to 0 at some point. The problem with Metropolis-Hastings doesn't really diminish to 0 fast enough. So we get a pretty big positive number in the denominator here, and that eats our nominal sample size pretty badly. And our effective sample size in this case was like 10% of that, which is passable, but not great. questions about effective sample size. And really, like, we'll talk about Stan on Thursday. But like the great thing about Stan is the effective sample size is like much higher than it would be with Metropolis. Questions? Okay. So the other type of Markov chain Monte Carlo method that is historically important is known as the Gibbs sampler, which can actually be seen as a special case of Metropolis-Hastings, where the proposal distribution, whose PDF is Q, is defined as the full conditional distribution that you're trying to draw from. And so full conditional distribution, what do I mean by that? I mean the distribute, now I'm using K in a different way, but the distribution of the kth element of theta given all the other elements of theta except the kth. So the conditional distribution of one thing given everything else. And if we use that as our proposal distribution, then you can show that alpha star is always 1. And so those proposals are always going to be accepted, even though there's no tuning parameter or anything like that to tune. And so you can get a valid algorithm Markov process by just looping over K, which is the number of parameters that you have, each time drawing from the full conditional distribution that's implied by the target distribution that you want to draw from, and then just go round and around like that. Now that presumes that you, one, recognize what all of the full conditional distributions are, like what their names are, and you have an algorithm to draw from each of those full conditional distributions. And so if you construct things just right in kind of simple models, you may be able to recognize what all of these full conditional distributions are and say, like, that's a gamma, that's a normal, like whatever it may be. You sort of have to choose the priors to be somewhat conjugate to the likelihoods in order for all that to happen. But most of the time, you're going to run into a situation, at least one of your parameters, you can like write down what the full conditional distribution is, but it doesn't have a name. And so you don't have an algorithm to draw from it. So you have to do like a Metropolis step within a Gibbs sampler in order to handle that one where you don't know how to represent the full conditional distribution, et cetera. And that can really destroy the efficiency. So in some cases, you can prove that a Gibbs sampler is really good and really efficient. But there's not that many cases where you can prove that to be so. And in most of the cases, we just sort of can't prove that it's really efficient. And if we can't prove it's really efficient, it tends to be really not efficient. And so in some cases, a Gibbs sampler works great. In other cases, not so much. And so here's how a Gibbs sampler would look for a bivariate normal distribution. Initialize X, make my empty matrix. I calculate beta, which is the coefficient when Y is regressed on X. I calculate lambda, which is the coefficient when X is regressed on Y. And I calculate the corresponding conditional standard deviation. And the thing to recognize here is now I have this sigma xy, the conditional standard deviation of X, given Y, which is the marginal standard deviation of X multiplied by the square root of 1 minus rho squared. And so that's going to be less than what marginal sigma X is when I multiply those two things together. Consequently, when I do this Gibbs process, the conditional standard deviation of X is going to be smaller than the marginal standard deviation of X in my original explicit algorithm, where I just do marginal of X, conditional of Y given X, marginal of X, conditional Y given X, S times in order to get S independent draws. Now I'm doing this ping pong thing where I draw from Y given X and then use that realization of Y to then draw from the conditional distribution of X given Y. And then I draw from Y given X and then X given Y. Do that whole thing S times. But the conditional standard deviation is of X given Y is smaller than the marginal standard deviation. And that's where the dependence and the lack of efficiency come in. But anyway, I can do this. I can return my matrix of draws. I can, get 1,000 of these. Doesn't require any tuning parameters. And when I make the plots of it, it sort of intuitively looks like this is mixing faster than in the Metropolis case, where it would sort of stick in the same place for 50 iterations and otherwise kind of move haphazardly around. In this case, just sort of you have an intuitive sense just by looking at it that it's getting where it's going at a fewer number of steps. It's more efficient. And indeed, if you calculated this, you get an estimated effective sample size of about 300 on a nominal sample size of 1,000 for S. So that's 3 times more efficient than Metropolis-Hastings for this example. But that's because I know the conditional distributions, the full conditional distributions for a bivariate normal. They're also just conditionally normal. If I didn't know one of the full conditional distributions and I had to do something else to account for that one, it could really undermine the efficiency of this process, and I could get back down to like effective sample size of 100 or maybe even less, really easily in more complicated settings than this. And so this is better in this case than Metropolis-Hastings, but still, 3 times worse than independent draws, if it's possible to obtain independent draws. So if you could obtain independent draws, you always would, pretty much. But there's just so few situations in which we're going to have an explicit algorithm to obtain independent draws from a posterior distribution that we have to resort to one of these Markov processes, which gives us dependent draws. And then the question becomes, how dependent are these draws? How much efficiency do we lose by utilizing an algorithm that doesn't give us independent draws? And the answer to that, it can be a lot for Metropolis and also for Gibbs. But for Stan, it tends to be a lot better. So we'll talk about that on Thursday. Last thing I want to talk about, and actually finish more or less on time today, what the Bug software does. So Bugs got started in like the mid-1990s. It was sort of the first general purpose Bayesian software. It stands for Bayesian sampling using, or Bayesian analysis using Gibbs sampling. It's also kind of buggy, so it was sort of a joke. But anyway, it was the first Bayesian software, general purpose. It came out in like mid-90s for Unix, of course. So like not that many people were capable of using. But then like 2001, 2002, something around, they came up with a Windows version. And back then, like everybody had Windows. And so the Windows version was sort of the first time that like a lot of people could use a Bayesian software. It's later evolved into like JAGs and OpenBugs more recently. Anyway, this R function is sort of an emulation of what Bugs does. Bugs is a little bit more intelligent than this, but not that much. And so I'm going to define a Bugs-ish function in R that takes another function that evaluates the log kernel of the posterior that I want to draw from, and a starting vector of parameters theta. I'm just going to set up a matrix to hold this draws. And then I'm going to loop over S, number of draws that I want, loop over K, which is the size of theta, the number of parameters that I want. And inside my double loop, I'm going to define another function that only depends on the kth element of theta. So this is a univariate function. And I'm going to evaluate my log kernel function that I pass in, which can be like whatever posterior distribution you want. It's logarithm kernel that's going to keep all elements of theta the same, except inserting theta k in the middle here. And then that's my full conditional function. And then this R uniron package will approximate the inverse CDF of that full conditional distribution and then draw from it. So I get a draw from theta k given theta not k. And I just loop all that over k, and then I store my realization of theta, loop that over S. Eventually I get S draws from the posterior distribution whose log kernel I define. This goes really slow, and bugs is a little bit more optimal than this. It does like pattern recognition to figure out when it might have an explicit full conditional distribution it can draw from. But this is like what bugs falls back to when it doesn't recognize what a full conditional distribution is. Anyway, if I call that, it runs like extremely slowly, which is like how it was before there was Stan. So you just had to like wait for days or whatever for it to finish. This doesn't quite take days. It takes like 10 minutes or so. But anyway, you get draws out. They look okay in terms of mixing. Not quite as good as the give sampler I wrote before, which took advantage of the fact that I know the full conditionals for a bivariate normal. Here I was like pretending I don't know what the full conditionals are. I just gave it the kernel of a bivariate normal and said like, bugs figure it out. And it did, but you get effective sample size about 200 on a nominal sample size of 1,000. So not quite as good as my customized give sampler. Certainly not as good as independent draws from a bivariate normal, but better than Metropolis-Hastings. And I didn't have to mess around with tuning parameters, which makes people happy. So this was like a very important historical step forward with the bugs project, but it's been largely superseded, although not everybody has gotten the news yet, but largely superseded by Stan, which is like really the most important MCMC algorithm of the last decade. And so we'll be talking about that on Thursday after we talk about the homeworks. So I'll see you then.